Imagine an electronic switch that can handle significant power, but once turned on, it stays on, almost like a digital latch. Understanding how this powerful switch behaves under different conditions is crucial for designing reliable circuits. The Silicon Controlled Rectifier, or SCR, characteristics curve defines the precise relationship between the anode current and the anode to cathode voltage, showing its distinct operating regions and switching behavior. This curve reveals how the SCR transitions from an off state to an on state, and, critically, what conditions maintain that on state. At its core, an SCR is a four-layer semiconductor device, structured as PNPN, which gives it a unique bistable characteristic. The curve illustrates three primary operating regions. First, the reverse blocking region shows the SCR acting as an open circuit when a negative voltage is applied across its anode and cathode, much like a reverse biased diode, up to its reverse breakdown voltage. Second, the forward blocking region occurs when a positive anode to cathode voltage is applied, but the gate current is zero or insufficient. Here, the SCR blocks current flow until the forward breakover voltage is reached. At this point, internal regenerative action, often initiated by sufficient gate current or high voltage, abruptly switches the device into its third state, the forward conducting region. Once in this region, the SCR behaves like a forward biased diode with very low voltage drop and high current flow, and it will remain in this state as long as the anode current stays above a critical value known as the holding current. For engineers, interpreting this curve is essential for designing circuits that effectively utilize SCRs in applications such as motor control, light dimmers, and power supplies. By analyzing the forward breakover voltage, you can determine the maximum voltage the device can block before unintended turn-on, while the holding current dictates the minimum current required to keep the SCR conducting once triggered. This allows for precise selection of the SCR and appropriate gate drive circuitry to ensure reliable and safe operation within its specified limits. A key distinction often overlooked is between holding current and latching current. While holding current is the minimum anode current to maintain conduction, latching current is the minimum anode current required for the SCR to remain on after the gate signal is removed. The latching current is always higher than the holding current, and understanding this nuance is vital for correct triggering and commutation circuit design, especially in pulse-based applications where the gate signal is momentary. Mastering the SCR characteristics curve empowers you to confidently design and troubleshoot high-power switching circuits. It provides the roadmap for predicting how the device will respond to varying voltage and current inputs, ensuring stable and efficient control in your electronic systems.